Operational amplifier anatomy tutorial sheet. Question 1. The circuit of figure 1 shows a simple form of op-amp circuit. Estimate IE, I1, I2 and I3, assuming that VI is 0 volts, V plus is 0 volts and V minus is 0 volts and VA is 0 volts. And it gives some solutions. So let's have a look at the circuit in question. We'll have, let's draw it in here, I'll do the calculations over there. (150 kiloohms) going into a long-tailed pair, or a differential amplifier if you prefer. VI, that's V plus, that's V minus, and we've got a 15 kiloohms here, and that goes down to a common emitter amplifier, which is driven from one leg of the one collector of the differential pair. This is 14 kiloohms. We'll call it R1. This is RE, 150k. That's RVA, 15k, and that drives a push-pull of common collectors, or if you prefer, emitter followers. Yeah. There we go. And the output's taken from here, and there's a load which is 2 kiloohms, RL 2k. And this is plus 15, and this is minus 15. It's not very narrow. There we go. Dot there, dot there. Oh, this is VO. This is VA. VO1 just here. And just for clarity, T1, T2, T3, T4, and T5. And we're calling this VO4. And this is VA. It's a little a, by the way. Yep, I think that's it. Fine. So I'll put on some currents as well, just because the question will ask about currents at some point or another. There's a current here which is I3, and the current here which is I1, and the current here which is I2, the current here which is IE. And that's it for now. Alrighty. So estimate IE, I1, I2, I3, assuming essentially 0 volts everywhere. So what we're asking for is the quiescent conditions. So there are a lot of ways to tackle this, and it's more or less your choice about the order. But I'll start on the same order as the sheet because it means the two things tally up quite well. And we'll start by dealing with the quiescent current in the differential pair. So for IE, you would, easiest method is to say, well look, this is 0 volts. So I'll draw it in blue, because then it will look different to the diagram. This is 0 volts. This is 0 volts. If they're both 0, and all these transistors should be in their forward active region, possibly except 4 and 5, which should be off unless there's a signal, there must be 0.7 volts here. And if there is, this node must be at plus 0.7 volts with respect to ground. as a consequence, if this is at plus 15 with respect to ground, and this is at plus 0.7 with respect to ground, across here we've got 14.3 volts. And if we do, tell you what, I will do the across voltages in green, and with respect to ground voltages in blue, because that will make it a little bit clearer as well. .3 volts across the 150 kiloohms, and then it's just a case of using Ohm's law, and we'll say that IE is equal to, I'll call it VRE upon RE, so the voltage across RE divided by the value of RE, which is 14.3 divided by 150 kiloohms. And if you've got a calculator to hand, or if you can do it in your head, even better. You should be able to get a decent estimate in your head, because this is about 150 E3, that's 50 E1, so 115 E1, sorry, so you can do it if you want to, but just to be accurate, just about 100 microamps or so, 95.3 microamps. So having got our IE, we'll have a go at I3. Now I3 we can say, well, if I know that this point here, the output is at 0, it should be at 0 because neither of these two will be conducting, so there's no chance of any current through RL, no chance for any current through RL, there shouldn't be any voltage across it because Ohm's law applies, so this point will be at 0 volts with respect to ground. If that's the case, this transistor should be off because we think that VA is ground as well. Looking at the question, it says VI is 0, V plus is 0, V minus is 0, and VA is 0, VA being this node here. So should be 0 across that, that's not conducting. If this is 0 as well, because these two are linked together, then that's 0 volts. So neither of these transistors are conducting. If that's the case, no voltage across there, and this ends at 0, we'll have 0 volts there as well, which will leave us with 15 volts across our VA, because we've got power supply and 0 at the other end. So we'll do I3 is V over R, where it's 15 upon RVA, which is 15 upon 15 k ohm, which is 1 milliamp. And this gives us the collector current for T3. Now, there will be some base current flowing in T3 because of the HFE relationship between IC and IB. So this will be, I'll call it IBT, IB3 we'll call it, IB3. And I'm going to assume that the HFE for this transistor and for all the transistors is 100. So we'll say IB3 is equal to IC3, which is just another way of saying I3, so I'll call it I3. I3 divided by HFE, where it's a little h, a big F and a big A, and that will be 1 milliamp divided by 100, which will give us 10 microamps. Now that 10 microamps is flowing down here, and here we go. I know that I've got to have a voltage across this resistor which is equal to the VBE of this transistor, which will be 0.7 volts. This base emitter junction here and the voltage across R1 are parallel with each other, so that will be 0.7 as well. So I know that I can work out what the current is in R1. I can work out this current, I call it IR1. And that will be, just apply Ohm's law again, so I have IR1 is equal to V upon R, which is 0.7 volts, divided by 14 kiloohms, which is 50 microamps. Pretty sure. Yeah, 50 microamps. Right. Now then, about I1. I1 flows down here into this node, and IB3 leaves the node and IR1 leaves the node. So if I wanted to, I could write a node equation to sum the currents at this node, and I'd be writing I1 equals IR1 plus IB3. I don't think I need to write that out as an equation on the screen, but you would apply a node equation on this node. So IR1 is the sum of that and that. Well, I know what those two things are, so I can write it out now. I1 equals to, I will write it, IR1 plus IB3 equals 50 microamps plus, go down here, plus 10 microamps, which is 60 microamps. So IR1 60 microamps. Right. We'll have to remember those, because they've got to go. What about IR2? So we know I'll put I1 is 60 microamps, which is what we just worked out. IR2, well, so not IR2, I2. I2 is IE minus I1. Now I've just worked out I1 and IE are, so this one shouldn't be too taxing. These two currents will sum to IE. If you're unfamiliar as to why that ought to be the case, have a look in the lecture notes on differential amplifying, the op amp anatomy, and you'll find it there. So we're just summing the numbers now. I2 is 95.3 microamps. Sorry, that's microamps. Minus 60 microamps. What will that leave us with? Just a bit less than 40 microamps. It's 34.7 microamps, is it? Did I get that right? 35.3. How did I do that wrong? So have a quick look, see if I can't subtract properly. 95.3, E minus 6, minus 60, E minus 6, 35.3. Yes, apparently I can't subtract properly. Never mind. 35.3 microamps. Right, okay, fair enough. And that is it for that question. Part I, anyway. We've got 1 milliamp from I3, which I haven't written on the board now because I've rubbed it off, but I3 was a milliamp. It was 15 volts divided by 15 kiloohms because no current there, so that's 0 volts. This 0 volts, so these two 0 volts. 0 volts at both ends of that transistor is switched off. Consequently, 0 volts there, 15 across the resistor, perform Ohm's law. Righty, on to part 2 then.